Okay, so let me just start with a comment. This was definitely the hardest chapter that we've had so far. So, not a bad idea if you try to review the lecture a few times and also try to think of some of your own calculations that you could do and put a real effort in trying to solve the problems for this chapter nicely. That's the best way to learn it. So I want to discuss a couple of things that are going to come up in the problems. So one of the things that I've asked you to study in the problems is I've asked you to study the commutation relation that we obtained from the harmonic oscillator and to study the Lorentz transformation properties of this commutation relation and to comment on it. And then the same thing for the Lorentz invariant version. Okay, so let's just talk about what are the main ideas. So first of all, if you study the Lorentz transformation properties of this commutator, what you are going to learn is that the right-hand side is not Lorentz invariant, okay? So the right-hand side is not Lorentz invariant. It turns out that it is invariant under rotations, but it's not invariant under a boost. So if we write this equation in one frame, and then we boost to another frame to find what equation we should use in the second frame, in fact, that equation will be different. So this means the right-hand side of our commutation relation is frame dependent. Now, of course, this equation, this commutator relation, this is the equation that we use to solve for what the oscillators are. If the right-hand side is changing in different frames, it means the oscillators that we use depend on the frame that we're in. So this means different inertial observers. So different inertial observers, and this means, observers in different frames, different inertial observers use different oscillators. Now, of course, there's nothing actually wrong with doing this. You can use those oscillators, but it means that it's not obvious that your theory is going to be Lorentz invariant. And at the end of the day, when you check Lorentz invariance and you discover that actually all of your predictions are Lorentz invariant, it comes as a bit of a shock. It's a bit mysterious. You don't know why you have this Lorentz invariance. On the other hand, if you use the second commutator shown, so the Lorentz invariant commutator, in this case, the right-hand side is Lorentz invariant. And that means, whatever inertial frame you're in, you have exactly the same commutation relation. And that means all inertial observers use the same oscillators. And the big advantage of doing things like this is that it's obvious why you get Lorentz invariant answers. It's obvious that you have built the theory in a Lorentz invariant way. So it's, I think, a much better formalism to use because you make Lorentz invariance manifest, okay? So maybe that's a good comment to make. So for this first set of commutators, Lorentz invariance is not manifest. So you might have a description consistent with Lorentz invariance, but it is not manifest. In the second description, Lorentz invariance is manifest. And this is why it's useful to work with those relativistically normalized oscillators. Okay, so that's the idea. The next thing I wanted to discuss, so imagine that you have a vector, x mu, so some time and some position, and let's imagine that this is a space-like vector. So what do we mean by that? Well, if you calculate x mu, and remember what this is, it's t squared minus x dot x, then this is less than 0. That's what it means to be space-like. So when we say space-like, we mean less than 0. Good. Okay, so let's just draw a space-time diagram. Here is t, here is x. Then this vector x mu would be something like this. The spatial component of the vector is much bigger than the temporal component of the vector. That's the point. Okay. What you have to do is construct a Lorentz transformation that takes x mu into minus x mu. And remember, it's only possible to find such a Lorentz transformation, so only possible for a space-like vector. If your vector is either time-like or light-like or null, so light-like and null mean the same thing, but if your vector is time-like or light-like or null, you cannot use a Lorentz transformation to change it into minus itself. That you can only have for a space-like vector. Let me maybe just write one more thing. So this condition over here, the condition that this is negative, we can call R to be the mod of X, and then that's the condition that R is greater than T. Okay, good. So I'm going to suggest to you how to find this Lorentz transformation. So what we do is we'll start off with our initial 4 vector. So it's t and x. And then the first thing that you can do, you can perform a rotation. Let's call it r. And then after the rotation, your vector lies along the positive x-axis. So you're just doing a rotation. That's not too difficult. Next, you will do a boost. Let's call it B for boost. And after the boost, this vector has got no temporal component. It's got the value A. And then for x, its y component vanishes and its z component vanishes. Next, so this was the first thing you did. Second thing you did. The next thing that you should do, so step number 3, is rotate in the xy plane by pi radians. And if you rotate in the xy plane by pi radians, well, that just turns the vector into minus itself. Then the fourth thing you can do is do the inverse of the boost B. In that case, the boost took you from TR naught naught to naught A naught naught. So the inverse will take you to minus TR naught naught. And then the fifth step that you can do, do the inverse of R. Okay, so we've broken this Lorentz transformation up into a sequence of steps. There's a rotation. You must work out what that rotation should be. There's a boost. Work out what that boost should be. Compose that with a rotation in the xy plane by pi radians. and then use the inverse of the boost in the inverse of the rotation, and that composite transformation will take any space-like vector into minus itself. Now, why do we have to restrict ourselves to a space-like vector? Well, when you do this construction, one of the things that you should check is, in this step over here, A is equal to the square root of r squared minus t squared. And that's only real if r is greater than t. Let's just make a comment that if x mu was time-like, then by using a boost b, you could get x mu into the form a tilde, comma naught. And what would a tilde be? A tilde would be the square root of t squared minus r squared. So that you could check. And finally, you could also check that if x mu was null, the best you could do would be to get x mu into a form like this, a naught naught, and a could be anything, okay? So by doing an appropriate boost, you can make a to be whatever you want. So to have a Lorentz transformation that takes x mu into minus x mu, your x mu has to be a space-like vector. Good. Okay, I hope that's enough of a hint for you to be able to construct this Lorentz transformation. We'll continue in a moment.